This time, this will be a little difficult. We will learn the directional derivatives and the gradient vector. So we have learned the partial derivatives. This is a special derivative. It's in the direction of x-axis or in the direction of y-axis. But now we want to know something different. We want to give a vector that satisfies in any direction. So we want to find directional derivative. Here, we recall that the partial derivative of fx and fy is defined as follows. There, if the derivative for x, so there is adding an h for x, and then y haven't changed, and then divided by h. The limit is for the derivative of x, and if for y, so the change is for y. This is special case, and this represents the rate of change for z in the direction of x and y directions. That is in the direction of the unit vector I. This is for x direction, and j. This is for y direction. So here that we have learned is two special cases in the direction of x and y direction. Okay, now we want to know something in any arbitrary direction. Because we now wish to find the rate of change z at x0 and y0 in the direction of an arbitrary unit vector u equal to a and b. So this is a unit vector. So the length of u equal to 1. To do this, we consider a surface S with the equation z equal to this one. This is the surface, and we let this one equal to f0 and y0. Then we have a point P. We have a point P lines on S. We see this figure. U equal to AB. We can see here. We suppose the angle of this is theta. Then the length of this part is sin theta, because the length of u equal to y. Because so this one is sin theta multiply 1, and this length is cosine theta multiply 1. So we can write it in this case. So it's cosine theta and sin theta. So A equal to cosine theta, and B equal to b theta. Now we focus on the point P. We see this figure. There is a vertical plane that pass through the point P. So there is a plane. This is a plane with the red color. This is the point P. So the plane passes the point P, and in the direction of U. So here is the direction U. So here is U. And there is an intersect. The intersect is the surface, so the blue color, with the plane, so is the red color. And the surface, the intersect is the curve C, So this is the intersect. This is the curve. This is the C. Here, we can do a tangent, a slope. Okay, we see here. The slope of the tangent line T here, the red color line is the slope of the tangent line. So the slope at the point P of the curve C is T. This is the T. And this one is the change of z in the direction u, If q is another point, we have another point q here on c, and p pim and q pim are the projections of p and q on x plane. So they are the p pim and q pim. They are the projection of p and q and q. Then the vector p pim and q pim is parallel to u. So here we find that p pim and q pim is parallel to the vector u. If they are parallel, then we have this following formula. So p pim q pim equal, there is a scalar h multiply u. We know u equal to a and b. So it's HA and HB. HA and HB. So it's okay. It's okay.
Yes.
Here is I think it's not easy. Okay. We know the point P is x0, y0, and 0. And Q pim is x, y, and 0. So we see here P pim and Q pim. And then we can get the vector P pim and Q pim is x minus x0, y minus y0, and 0. So it's equal HU. We know U is H multiply A and H multiply B. Then from here we can get this one. X minus x0 equal HA, and y minus y0 equal HB. And then we can get x and y. So here, then we want to then we can get this one. Delta Z divided by H is Z minus Z0 divided by H. And Z is this one. Z is x0 plus HA, y0 plus HB. So this point. And minus F0, Fx0, y0. So this point. And divided by H. So here, delta Z is the length of this part, and H is the length of this part, and the Z divided by H, so is the tangent of this corner. So if we take this one, is alpha. So we have tangent alpha equal to this one. Since there is perpendicular, and so here is also perpendicular. Okay. Are you okay?
Okay, teacher.
Okay, so we get the change rate. This is the change rate. So we have the following definition. This is the definition for the directional derivative. If we take the limit at h approach 0, we obtain the rate of change c in the direction of u. So here, the directional derivative of f at point x0, y0 in the direction u is defined like this one. So here g means the directional derivative, and in the direction u for f at the point x0, y0 is defined as a limit. So the limit is h approach 0. This is delta z. divided by h, and there they equal fx0 plus ha, y0 plus hb minus fx0 y0. If this limit exists, then we call it a directional derivative. So this one should be remembered. You can keep this one, write this one in your notebook. This one, this question. Okay.
Okay, sir.
Okay. So this is the definition for directional derivative. Okay. But comparing different two, here is the definition two. So this is the directional derivative. And the equation one. Equation one is the partial derivative with x and y. With x and y. With that, if u equal I equal 1, 0, and then the directional derivative in the direction I will equal to fx. So we take a I in this one. So a will equal to 1 and b will equal to 0. This one, a equal to 1 and b will equal to 0. And then we can get the first one. Yes? Okay.
Okay, sir.
Okay, and then if u equal g and g equal 0, 1, then the directional derivative in the direction c will equal fy. So in this case, a will equal to 0 and b will equal 1. And then we will get the second case. So fx and fy are several cases of directional derivative. In other words, partial derivative of f with respect to x and y are just several cases for directional derivative. If we want to compute the directional derivative, we have used the following formula. This formula. Okay, if f is a differential function of x and y, then f have a directional derivative in the direction of any unit vector u equal a and b. And then the directional derivative of f in the direction u equal the partial derivative of x multiply a and the partial derivative of y multiply b. So here a is the formula for compute the directional derivative. So this one is also important. So please write this one in your notebook also. So please write this formula. Write this formula in your notebook. We have to use this one to compute the directional derivative. So if we can get the partial derivative for x and for y, we can get the directional derivative. Okay.
Okay, sir.
Okay. If the unit vector makes an angle theta with a positive x-axis, then we can write this one. I have explained in front. And the formula is series 3 of this one. We have write it. We can write can be writing will become this one. So A will become cosine theta, and B will become sin theta. Okay.
Yes, sir.
Okay, there is an example. Find the directional derivative of f. F is this one. And u is the unit vector given by an angle theta equal to pi over 6. So find the directional derivative at the point 1 and 2. So with the formula we have write in your notebook, we can get the partial derivative of with respect to x and y. And then with these two, we can get the directional derivative. Okay.
Okay.
With the formula this one. With the formula this one. Yes.
Yes, sir.
Okay. So we have to find the partial derivative of fx and fy, and we also have need to use the cosine theta and sin theta. So please use this formula. Use this formula to get the directional derivative at the point 1 and 2. 1, 2. Okay. So please do it by yourself. Okay. Anyone have finished?
Wait, sir.
Okay.
No, sir.
Okay, please answer if possible. So the derivative, the directional derivative of f is who finished? Anyone can answer? Chloe can answer. Or you finish?
3x squared.
3x square. Yeah, 3x square. And then
Minus 3y.
minus 3y. Yeah, 3y. So it's we use this formula. So the this one is 3x square and minus 3y. And then multiply this one. Yes.
Yeah.
Okay, and then for the derivative for y is
Negative 3x
minus
plus 8y.
8y. So this one, yes.
Yes.
And then multiply sin pi over 6. So it's 1 over 2. Okay.
Yes.
And then we can get this one. You can get this one. And then we take x equal to 1 and y equal to 2. We get in this formula, and then we can get this one. X equal to 1. So here x equal 1 for 1. And then y equal to 2. So we take 2 here. And then we can get the final result. Okay.
Mhm.
Okay. Everyone is okay?
Yes, sir.
Okay. So another definition is the gradient vector. Gradient vector. So there we get the dictational vectors. There is a faster increase, decrease direction. So we have find the special direction. The special direction is a gradient. Okay. Notice from theorem 3 that the direction derivative of the direction function can write as a dot product of two vectors. So we have learned dot product. So the directional derivative can write like this one, and then we use the dot product to express, and then we can get this one. So the first vector in the dot product occurs not only in computing directional derivatives, but also in many other contexts. So this one, this part is important. So we give a special name. It's called the gradient of f. The gradient of f. And a special notation like this one. This one also called the delta f. Delta f. We use delta f to means the gradient of f. The gradient of f. Okay. So this is the definition. This is the definition for the gradient. Then it gives the if f is a function of two variables, x and y, then the gradient of f, is a vector function, delta f, is defined as follows. Delta f equal fx, fy, fx, fy. So this is the partial derivative with respect to x, and then here is with respect to y. And we also can write like this one. So here, this one is the definition for the gradient. Okay.
Okay.
Okay, here is an example. Find the gradient of f at this point. So we have to use the formula. Okay, please do it. Try to do it by yourself.
Can you show formula again?
This formula. Okay, use this formula. You possible write it in your notebook. Okay.
Yeah.
Okay. So use that formula to do this one. Finished?
No, sir.
Okay,
Yes, sir.
this is easy, yes?
Yes, sir.
Okay, please answer if possible. Gradient f equal Lookman, can you answer?
Yes, sir.
Okay. Gradient f, the delta f will equal
First we have to take derivative with respect to x, then y will be constant
the derivative for x equal
minus cos x.
minus no minus
No minus.
no minus
Okay, cos x plus
cosine plus
plus y into
y
e raised to power xy.
so this one
Yes.
is the first one is cosine plus y dxy. Yes, this one.
Yes, sir.
And for
And
y,
for y, x into e raised to power xy.
this one x and exy and exy. Okay, and
Yes.
then we take x equal 0 and y equal 1 in this formula. We get here x equal 0, y equal
Yes.
1 into this formula. We get the final result is how you get? Go.
I am doing this. Wait.
Just x equal 0. See, so here cosine 0 equal 1. Yes.
0 equal 1. Yes, sir.
And then take this one x equal 1 and y equal 0. So this is 0. Yes. No, this one. This is 1.
1.
This
It
is 1.
will
1
be
plus 1 is 2. Yes.
2 and 1. The answer is 2 and 1.
2 and 1. No, here is 0.
No, 0. 2 and 0. Sorry.
2 0
Yes, sir.
and 0. Because here is x equal 0 and we take here is 0 multiply 1. So it's 0.
Yes, sir.
Okay. And then it's the notation for the gradient vector. So this one we can rewrite the expression 7 for the directional derivative in this form. So the directional derivative of f equal the gradient f dot this dot product u dot u. So this is another method to write the directional derivative. So here, the expression of the directional derivative in the direction u is the scalar projection of the gradient vector onto u. So here, if there is a direction u, here is delta f. So this is the delta f. No, this one. This one. Delta f. So if it multiply, so is this one. This is the good product. Yes. So it's a projection. Okay.
Okay, sir.
So this is a delta f to the u this part. Okay, functions of three variables. So here in front we give the directional derivative the gradient in two variables. So can extend this to three variables. So here three variables we can define the directional derivative as follows. So the directional derivative of f at this point in the direction of u is defined as a limit. The limit is h per 0, then x plus ha, y plus y0 plus hb, and z0 plus hc, and then minus f x0, y0, and z0, and given over h. So if this limit exists, we call it the directional derivative. So it is similar with the two variables. We just add a variable c, this one. So this is the rate of change. This is the rate of change in the direction u. And the u is a unit vector. Okay. If we
Okay.
use vector notation, any problem? If we use vector problem notation, so here we use vector notation, and then we give this formula, x0 plus hu minus f0 divided by h, and then this limit is the directional derivative, and here x, u are vectors. So here, if x equal x0, y0, this is for two dimensions. If x0 equal x0, y0, and z0, this is for three dimensions. Okay.
Okay, sir.
So here is easy. This is some different form. Yeah. If f is differentiable, and u equal this one, then the directional derivative for f will equal to this one, fx multiply a, fy multiply b, and plus fc multiply c. Gradient vector for the gradient vector denoted by this one, also this one, and equal this one, fx, fy, and fz, So for short, we can write like this one, So this is the gradient for three variables. There are three sections. The first one is fx, second one is fy, and the last one is fz. So there are three partial derivatives. Okay.
Okay, sir.
Okay. So this is the gradient for three variables. And then we can use gradient to rewrite the directional derivative. So this is the same as the two vector, two variable case. So the directional derivative will equal the gradient dot product u. So here is similar with two variable case. Okay. So this is similar as the two variable case. Another example, f equal x multiply sin x nyc sin yc. And first, you need to find the gradient of f. And then the second is to find the directional derivative of f at this point, 1, 3, and 0. In the direction v equal to this one. So the first you have to use the gradient formula. Yes? How you write it in your notebook? The gradient formula? So first you have to use the gradient formula. Is this one? Gradient formula, this one. This one, 13, 13. How you write it?
No, sir, that is right.
So please write this one. Write this one. Okay. And the second, we have to get the directional derivative. So we have to use this one. Okay. So this one also write it in your notebook. Okay.
Yes.
With these two formula to solve this problem, please. Solve this problem with the two formula that you have write in your notebook.
Mm.
Okay. Finish. Have finished?
No, sir, wait.
No. Now it's okay.
Done, sir, but not sure whether it is true or no.
It's difficult.
Sorry, sir.
It's difficult or not?
A little bit.
Sure.
I have done, but not sure it's right or no.
You get the gradient? Get this first one is okay?
Cos YZ.
Ferrous. It's okay for you? Ferrous. Zahid? Zahid, are you finished? No one finished. Clave, are you finished?
I'm not sure.
Okay, you can try the first one. The first gradient for f is
Cos
cosine.
YZ. Okay, I'm not sure.
You have write the formula for the gradient.
Yeah.
So can you give me the formula for the gradient f equal is equal
Derivative of x
yeah, derivative for x
plus derivative of y
yeah, plus the derivative for y and multiply c, and then plus
derivative of
the derivative for c. So we
z.
can use the formula. It's easy. So we use the formula, this one. So the first one is for the derivative for x, yes, and the
Yes, sir.
second for the derivative of y, and this is the for derivative for z. So this formula is easy for the partial derivative. So the first one is for
First one sin YZ.
yeah 7c, and the second one is
Second one is XZ cos YZ.
xz cosine yz. Yes, this one. The last
And
one is
third one is XY cos YZ.
yeah xy cosine yz.
Y.
Yeah, that's right. R is right.
Yes.
It's easy. It's very easy. You just take this means this one is easy.
Yes, sir.
And the directional derivative. So this one we know is equal the gradient dot product the u. Yes, dot product
Yes.
u. So here we have a direction v for this one. So we have to use this one to get the u. Yes.
Yes, sir.
We know u is a unit vector. Yes, a unit vector.
Oh, yes, sir.
So we have to unit it. So this one.
Find its magnitude.
And then we have to
Yes,
get
sir.
a unit vector in the direction v. Yes.
Okay.
So this one is u. This one is u. Can you get this one?
I
So
didn't
this one is the first one is 1 plus 2 square, 1 square plus 2 square plus
Yes, sir.
minus
One
1 square. And then this one is the first one is 1. Yes.
Yes, sir.
And then the second one is 2. The last one is minus 1.
Yes,
Yes.
sir. Okay, sir.
Okay. Yeah. Then we can get u. We get u. And then we know that directional derivative equal the gradient multiply dot product u dot product u. Yes.
Yes, sir.
So we take the point 130 in this formula. In this formula, we get this one 003 003.
Yes, sir.
And then this one dot product this one. We can get the value. Okay.
Sir.
So
Okay.
this one, the last one is a 3K, and the product this one. Then we know this one product this one is 0, and product is 0, and this one is 3 minus multiply minus 1 over square root 6. So the final result is this one.
Sir, I didn't get that the last two steps.
Here you don't know. Here, this one you don't know.
I know this, but 3K.
Yeah.
I don't 3K.
Here we get this one 003. Yes. This means 0 minus I plus 0 multiply
Okay. Okay.
plus 3.
Okay. Yes.
Yes.
Okay. Now I got.
Okay. Everyone is okay for this one?
Yes, sir.
Okay. So another part is maximizing the direction derivatives. Here, as I have said, there are many directions. There is a special case that is the farthest direction for the function increase or decrease. So it's so we know that where is okay, we start here. In which there are directions, these directions does f change the farthest, and what is the maximum rate of change? Here we can use this theorem to answer this question. This one. Suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative is the gradient, the absolute value of the gradient. And it occurs when u has the same direction as the gradient vector. Okay, so the farthest changes or the maximum rate of change is the gradient or the absolute value of the gradient. It's okay.
Okay, sir.
Okay. So here, if we want to this one, there is some example. F equal to this one. Find the rate of change that f at the point this point in the direction from P to Q. So here we want to find the rate of change. The rate of change means that is a directional derivative. So we want the first one is to find the directional derivative in this direction from P to Q. And then the second is to find the maximum rate of change. And then find the maximum rate of change. Here is find the direction, and then the second is find the maximum rate of change. Okay, can you do it?
No, sir. Can you show us.
So first one, so find the rate of change. What's the rate of change? So this is means find the directional derivative. Directional derivative. You still remember the formula for the directional derivative? This one equal to what?
Moderator.
Yeah, fxy del fxy into dot product vector unit vector.
No, it's equal to the gradient. Yes, the gradient of f. Dot product u.
Yes.
Yes. So first you have to find the gradient of f. Then you have to find the unit vector u. Okay.
Yes, sir.
Can you try to find these two one? The first one and the second one.
Okay. Sir,
Yeah.
what is the unit vector here?
Unit vector, you have see here, it tells you the direction. Yes, the direction is here. This is just the example for 5. We have the direction, and then we just need to find a unit vector of this direction. You still remember?
So no, in formula, what we will write in the place of unit vector?
So you have find this one, the gradient of f.
Yes, sir.
Okay, tell me.
E raised to power y.
Yeah, e by e for exponent y.
And x into e raised to power y.
Yeah, that's right. Then you get the direction.
I don't know how to get.
He said from P to Q, from P to Q, and P it gives here, and Q it gives here. And you cannot get the direction. P, Q, the direction of PQ. It equals this one minus this one, yes?
OP minus OQ minus OP. Yes.
So the first one is minus
Second one.
yeah, 3 over 2, 1.5, yes? And
Yes.
then this one minus this one, so it's the second one is 2.
Yes, sir.
Yes, with this direction, we can get the unit vector u. Yes. Yes.
Okay. Okay, sir.
Okay, try to do it.
Okay.
So,
Sir,
okay, this
it should.
Okay.
I'm doing this.
Okay. And then, as you have said, this is the gradient. Yes, this is the gradient. And then this is the direction. The gradient here with the gradient, we take the point. We take the point 2 and 0. 2 and 0, x equal to 2 and y equals 0, we get the gradient is 1 and 2. Yes, because y equals 0, so it's E0, E exponent 0 is 1. And here 2 multiply 1, so it's 2. Yes, so this is the gradient, okay?
Yes.
And then we get the direction. The direction is minus 1.2 and 2. So minus 1.5, sorry. So this one, yes?
Yes.
And with this one, we can get the unit vector u. We can get the unit vector u. And it gives this one. It gives this one. Have you get it? Got it?
Yes. Yes, sir.
Okay. And then we use the formula, this formula. So the gradient dot product u, dot product u. Yes, we have this one equal 1, 2, and this one equal this one here. Here, and then we take this one 1, 2 dot product minus 3 over 5 and 4 over 5. Yes.
Okay, sir.
And we get the final result is 1 multiply minus 3 over 5 plus 2 multiply 4 over 5 is equal to 1. Is equal to 1. So this is the first. This is for the first problem, and for the second problem, it's want to get the direction. Get the direction for. So here, the second problem is want to get the direction for the maximum rate of change. This one you get it. Okay, have you get it? This one, the direction. Yeah, the second one, the direction for the maximum rate of change. You still remember which direction is the maximum rate of change? Which direction? So the direction of the maximum rate of change is the direction of the gradient. Is the direction of the gradient. So here it gives. So here is this is the have the same direction of the gradient of delta f. Yes. So this is the maximum change of maximum rate of change. Okay. And the greatest the maximum rate is this one. Is this one. So the absolute value is the great and the maximum rate of change. So what we need is here. This one. And this one. Ct is the gradient. Yes. Okay.
Which one is gradient?
This one is the gradient. We have get it. We have got
Yes.
it. So we know the direction that f has has maximum rate of change is the gradient direction. Yes. It's the same as the gradient direction. So it's the direction is 1, 2, 1, 2. So here the second answer is easy. We have get it. It's 1, 2. And the maximum rate of change is the absolute value of the gradient. So it's this one, 1, 2. The absolute value is a square root of 5. So it's the length of the gradient. Understand here?
Okay.
So here we use the theorem 15. Use this one. This one. See this one is the theorem 15. F is a differential function of 2 or 3 variables. Then the maximum value of the directional derivative is this one. So this is the maximum value. So this is the length of the gradient. Yes. And this it occurs when u has the same direction as the gradient vector. So the direction is of u is the same as the gradient, and the maximum value is the length of the gradient. Okay.
Okay.
Okay. This is first. This is the point 15.5. 15.5. So this is all of this. Now we have finished this part. So please have a rest for 5 minutes. Okay. And the following we are learning another part. So another part is maximum and minimum. We are learning. Okay, rest for 5 minutes. Okay, rest for 5 minutes. Okay, we start again. Everyone is okay.
Yes, sir.
Okay. Now in this part we are learning the maximum and the minimum values. In fact, we have learned this part, learned them last semester for one variable case. Now we are extending it to 2 or more variable case. See this figure? In this section, we see how to use partial derivatives to local or maximum or minimum functions of 2 variables. To get, maybe here is a root 1 get, root get. We see this figure here. From this figure, we can find here, there is a point. This point is the absolute minimum of this figure. And here another point is called a local minimum. Local minimum. This point is absolute maximum. And this point is called local maximum. So in the following, we will give the definition for this point. There are 2 variable, 2 points AB where f has a local maximum. That is, FAB is larger than nearby values of xy, fxy. So this is called local maximum. The larger of these 2 values of the is the absolute maximum. So this is the absolute maximum. And for minimum, it's also the same case. So we see the exact definition. Exact definition here gives the exact definition. Definition 1: a function of 2 variables have a local maximum at AB if fxy is smaller or equal FAB. Then when xy is nearby near AB. So this point FAB is called the local maximum value. If fxy is bigger or equal FAB, then we call FAB. FAB is the local minimum value. So here is the local minimum, and there is a local maximum. If the inequality in definition 1 holds for all points, here is for all points xy, then it's called absolute maximum. So here, when it's hold for values near AB, we call it a local. If it's for all xy, then we call it absolute maximum. And in this case, if it's satisfied for all xy, then we call it absolute minimum. So here is the difference with local and absolute. This one is for all points. This one is only for the points near AB. Only AB, for the points near AB. So here is the definition for the minimum or the maximum. There is a theorem can tell us if it's a minimum or maximum point, and it has some properties. Here, famous theorem gives the properties. If f has a local maximum or minimum at AB, then the first order partial derivative of f exists. If this exists, then it will equal 0. it will equal 0. In fact, this is the same as the first variable case. If we know that if f a function f have a point x0, and this point 0 is a maximum or a minimum, we have this one fx0, the derivative of this one will equal 0, Now here we have two variables, x and y. So there are two partial derivative equal 0. Since this is was found by FEMA, so it's called FEMA theory. Okay. Everyone okay?
Okay, sir.
Okay, this is the definition and the property for the maximum and the minimum. The point AB is here is definition for critical points. A point AB is called a critical point or stationary point if f the partial derivative equals 0, if the partial derivative equals 0, or one of these partial derivative doesn't exist. These two cases are called critical point. So theory 2 says f has local minimum or maximum point at AB, then AB is a critical point. It's a critical point. Yeah, as in single variable calculus, not all critical points give rise to maximum or minimum. Yeah, a function could have a local maximum or local minimum or neither at a critical point. It could be a maximum or a minimum or neither. I can give an example such as f x y equal x multiply y at the point 0, 0. At this point it is a critical point. It's a critical point, but it couldn't give a minimum or maximum. Since this one, okay. There is example 1. Find the maximum and all the minimum value of this function. So you can try to do it. This is a two variable case. Okay, have finished?
No, sir.
No, you just need to get the partial derivative of first order and let them equal 0. Yeah. We know if it's a maximum or minimum, it should have should be the first order partial derivative equal 0. Yes.
Well, we have to find the derivative with respect to x and y,
Yeah.
and then let them equal to 0.
Yes.
So then x and y, values of x and y we will get.
Yes.
Okay, I have got.
You have got okay. The partial derivative with respect to x will equal
2x minus 2.
2x minus 2. Yeah, that's right. And then with respect to y,
2y minus 6.
2y minus 6. Yeah, this 2y. And then we let this 2y equal 0. We get x equal
X equal 1.
y equal
3.
3. So it's we have a critical point. It's 1, 3. Yes.
Yes.
1, 3. And then we take this one in this formula. We can find the maximum or the minimum value. You take this one in this equation, you get
Okay.
so we can do it together. Okay. This formula, we can change it. We can write it like this one. We write it like this one. Okay.
Well,
Okay. We can rewrite it like this one. Yes.
Yes.
So here x square minus 2x is can write x minus 1 square, this one, and then it's need a 1, so it can get from here. Okay. Okay. And then y square minus 6y, and we can write it's y minus 3 square, and then it need a 9. It need 9, so we can get 9 from here. So we take 1 and 9, and then it left 4. Yes. Okay. Oh, good. So we get this one, and we know this one is bigger than 0. Yes. And this one is bigger than 0 also. Yes.
Yes.
So, okay. Make it look good. Then this one is bigger than 0, and this one is bigger too. So the function is bigger than 4, bigger and equal than 4. Yes. For xy. Then this point 1, 3 is a local minimum. Is this one is a local minimum point. Then we take 1, 3 in this function, we get 4. And then in fact we can get the figure like this one. And 1, 3 is in here. 1, 3, 4 is here a point. It's not good. So this is a local minimum. In fact, it's a brute minimum. It's a from this one. Okay, we can see now. Yes,
Yes.
this function, we can rewrite it like this one.
Okay,
Yes.
sir.
So we can find this one is bigger than 4. Because this one is positive. This one is positive. So it's bigger
Yes.
than 4. Yes. So we take this point in this to find it's equal 4. Equal 4. Yes.
Okay.
So this point is absolute minimum by this figure. This figure. Okay. The following test is analogous to the second derivative test for functions of one variable. Okay. Here is a method. There is a method to know if a point is a local minimum or local maximum. Okay, we see here. Is this should use the derivative of second derivative. Second derivative. Suppose the second partial derivative of f are continuous on a disk with the center AB, and suppose that the first partial derivative are equal 0. So then A and B is a critical point. Is a critical point. Yes. And then let G equal this one. F XX. So this is the partial derivative for X with the second derivative, and then this second derivative for Y. And then this is the second derivative for X and Y. So this one multiply this one minus the square of this one. We let this one equal G. If G is bigger than 0, and the first derivative for X, the second partial derivative for X is bigger than 0, then it's a local minimum. If G is bigger than 0 and the second derivative for X is smaller than 0, then it's a local maximum. If G is smaller than 0, then it's not a local minimum or maximum. So this is important. This is important for decide if a point is a local or minimum or maximum. So please write this one, this 3-1. No, this 3-1. This from this part your notebook. First, we have to define G is fx multiply fyy minus fxy square, and then use this formula to decide is a local minimum or local maximum or not anyone. Okay.
No, sir. Wait a minute.
No. Okay. Okay.
Okay, sir.
Okay. So give give a function. Give a function. If they let you to find the maximum or the minimum, the first step you have to get the first derivative. This is the first step. So you have to get the first derivative and let them equal 0. And then you get the critical point. The critical point. Yes, the critical point. So this point is here is AB to get the critical point. And then use this formula. Use this formula to decide it is the maximum or minimum. Yes.
Okay, sir.
Two steps. The first step derivative, first part derivative equal 0, get the critical point. And the second step, use this formula to know if it's the maximum or the minimum. Okay. Yeah, absolute maximum or minimum. Another one. Okay. For the function of one variable, the extreme value of value theorem said that if f is continuous on a closed interval, then f has an absolute minimum value and absolute maximum value. This we have learned in last semester. We have learned last semester. So if we want to find the maximum, absolute maximum or minimum, we have to check the critical point, and also the endpoint. So there are two parts. This is the first part, the critical point and the endpoints. Okay.
Yeah.
So okay. Another definition. This also have learned in the last semester. A boundary point of G is a point AB. So like this one. The point P, such that every disk with the center AB contain points in G and also points not in G. So like this one, there is a point P. It is called a boundary point because we have a disk. It have part in G. This part in G. Another part is not in G. Yes, this we have learned. For instance, the disk this one, x squared plus y squared is smaller and equal 0, which consists of all points on and inside of the circle x squared plus y squared equal 1. All points on and inside of the circle. So on the circle is the boundary point on boundary point. And it's a closed set because it contains all points of its boundary points. The boundary point is this one. Okay, but if even one point of the boundary curve were omitted, the set would be not be closed. Like this one, and this one is closed. And this one we omitted some points, so this one is not closed. And here omitted only one point is also not closed. And this one omitted some points here, and here, omitted some points, so it's not closed. Okay.
Okay.
Okay. Another definition is the bounded set. A bounded set, that means one that is contained within some disk. So it means that if here is a set, if we can find some disk can contain this set, then we call it a bounded set. Okay. In terms of closed bounded set, we can state the following counterparts of the extreme value theorem in 2 dimensions. This is for 2-dimension case. Extreme value theorem of a function of 2 variables. If f is continuous on closed and bounded set, so it's on a closed first and then is bounded set, then f attains absolute maximum value f x1 y1 and absolute minimum value f x2 y2. Okay, so it means if f is continuous on a closed and bounded set, then it can obtain absolute minimum and absolute maximum value. Okay.
Okay.
Okay. Here we have some following extension of a closed interval method. So here is the method to find the absolute maximum or the absolute minimum value. There are 3 steps. In fact, we have learned it. To find the absolute maximum or the minimum values of a continuous function. The first step is to find the value at critical points. The second step is to find the extreme value on the boundary. And the last step is compare. The largest of the values is the largest is the maximum, and the smallest of these values is the minimum. The first step is for critical points. Second step is for the boundary point. The last step is to compare all these values. Compare all these values. So this is the method. To find the absolute maximum or minimum values. Okay. Here is an example. Find the absolute maximum or minimum values of the function on the rectangle on this rectangle. So please use the 3 steps to find the results. Okay. You still remember the 3 steps? You remember the 3 steps?
Yes, sir.
Okay, please do it with the 3 steps. So it's okay. For the first, you find the critical point. Yes.
Sir, I'm unable to solve it.
Okay. We can do it together. Okay.
Yes.
Okay. Which step are you finished? Okay, we will do it. The first step, we want to get the absolute maximum or minimum. First step, we have to get the partial derivative of first order, and we let them equal 0 to get the critical point. So the partial derivative for x is 2x minus 2y. Yes. So for 2x, the first derivative is 2x minus 2y equals 0. And then the partial derivative for y is 2x minus 2x plus 2 minus 2x plus 2 equals 0. So from this one, we get x equal 1. And then from here, we know x equal y. So x equal 1 and then y equal 1. Yes? Yes? Are you okay?
Yes.
Okay. Okay, so from here we get x equal 1, and from here we get y equal x equal 1. So we get a critical point is 1, 1, 1, 1. Then we take 1, 1 in the function. We get the value f1 equal 1. So here is the function x equal 1, and then minus 2 and plus 2. So it's equal 1. Okay. Here is the function. Yes. So here is the point, critical point. And then the second, this is the first step. And we also have to consider the second step is the point on the boundary. There are 4 boundaries. The first boundary we see here. There are 4 boundaries. The first boundary is x equal 1, and then the x equals 3. Another one y equals 0, and then y equal to 2. So there are 3 boundaries. Okay. Understand or not? Are you understand?
Yeah.
Yes, okay. So we have 3 boundaries. The first boundary, the second boundary, and the third one, and the first one, 3 boundaries. So this is the rectangle, and 3 boundary L1, L2, L3, and L4, 3 boundaries. So we have to consider the points on these boundaries. We take L1 is y equals 0. So we take y equals 0 in the function. Here is the function. We get so here is 0 and here is 0. So we only get x squared. We know x is bigger than 0 and smaller than 3. And this one is an increasing function. So this point is the smallest point, and this one is the biggest point. We take this one, f0, x here is 0, and x equals 0 is we take this one inside is 0. And here y equals 0 we cannot change, and we take x equals 3. So 3, 0 we take in this section in this function is 9. It's 9. Okay.
Okay.
Okay. So this is for the first boundary. And then for the second boundary, is x equals 3. We take x equals 3 in this function. So it's 9 minus 6y plus 2y. So it's 9 minus 4y. minus 4y. And you find this function is a decreasing function. It's a decreasing function. So this point is the maximum point, and this is the local maximum point. Local minimum point. So we take this point in this function. We get 3, x equals 3, and y equals 0. We get 9, 9. And we take x equals 3 and y equals 2. We get 1, 1. Okay?
Okay.
Okay. So this is for the second boundary. And then for the third boundary. The third boundary is y equal to 2. Y equal to 2. We take y equal to 2 in this function. And get x squared minus 4x plus 2x, 2y. Minus 4y plus 2y. So it's this one. No. Y equal to 2. This one equal to 2. And this is going to become 4. So it's x squared minus 4x plus 4. That's 4. And this function we know this is we can change it to like this one. X minus 2 square. Yes.
Yes.
So
yes.
this is the smallest point is 2. Is 2. So it's if x equal to 2 is in this interval. So it's the smallest one. Is 2. Is 2. X equal to 2 and y equal to 2 is 0. Is 0. And the maximum value is x equal 0. X equal 0. So because it's far from 2 than 3. Than 3. So in this one we take x equal 0, y equal to 2. In this equation, we get 4. Okay. So this is for the third boundary, and then the last boundary is L4. L4 is x equal 0. We take this one in this function, and we get this is 0, this is 0, and so there are only 2y. And this is an increasing function. So this is the minimum, this is the maximum point. We take inside, we get this is the maximum value is 4, and the minimum value is 0. Okay, then we compare all of these videos. On the boundary and on the of the critical points videos. We get the maximum value is 9 and the minimum value is 0. So yeah, step 3 will compare all these videos with the video f11 equals 1 and as the critical points, and conclude that the absolute maximum value of f on T is 9, f30 equal 9, and the absolute minimum value is f00 equal f22 equal 0. So here it's easy. Okay.
Okay, sir.
Okay. So this is the figure we can find. Here is a point, and here this is the minimum value. F00 and F22. There is also a minimum value, and not this point is the maximum value. Another problem is the Lagrange multipliers. Lagrange multipliers. Okay, in this section, we present Lagrange's method for maximum or minimum general function of a general function f subject to a constraint c. So this a method to find a maximum value of a function f in the constraint or under the constraint c equal to k. So this is this will be difficult than no constraint case. Because for two variables, it will be easier. So here we will focus on two variables at first. Focus on two variables at first. We seek the extreme value of f when the point of points xy is restricted to line on the linear curve cxy equal to k. So this is the constraint formula. Constraint formula. So here is okay. Find the extreme value of f with the constraint cxy equal k. So here is the figure shows the curve together with several layers of curve f. So this is the curve. The red color is the curve for f equal to some values from 7 to 11. From 7 to 11. And the blue curve is a function. Is a function. Cxy equal k. Okay. Okay, here in some explain. It's not easy to here it's not easy to understand. To the maximum f subject to k, c equal to k is to find the largest value of c such that the linear curve f equal to c intersects c equal to k. So here it's not easy. It appears from figure 1 that this happens when this curve just touch each other. That is when they have a common tangent line, like this point. This is a maximal. This is a maximal point. So this the blue line and the red line have the same tangent at this point. At this point. So they have a common tangent line. Common tangent line. This means that the normal line at the point x0, y0, where they touch are identical. So the gradient vector are parallel. That is this one. For some scalar lambda. So here we can find the normal line of the red color and the blue color are this one. No, this one. This is the normal line, yes. This is the tangent line. This is the tangent line. This is the normal line. At the point, at this point, x0, y0. So we have this. If they are parallel, then we have this formula. The formula. The delta f will equal lambda multiplied delta c. Okay.
Okay.
So we have this this formula. Delta f This is the for three variable case. For three variable case, it's the same case. So delta f equal lambda multiply delta g. If delta g, where lambda, the number lambda is called a Lagrange multiplier. So this one is called a Lagrange multiplier. So this one you can write in your notebook. This one is also important formula.
Okay, sir.
This is for the case x0, y0, and z0 is extreme value point. Is an extreme value point. Okay.
Okay, sir.
Okay. So the first year, based on equation 1 is here. The method of Lagrange multiplier. So this is the method to find the maximum or the minimum value. To find the maximum or the minimum value of f subject to the constraint g. Subject to the constraint g. The first step is to find the value of x, y, z and lambda such that delta f equal lambda g, lambda delta g, and c equal to k. So the first step is find these values with these two functions. And then the second step is to evaluate all these points. From step A, from the that result from step A, and the largest is the maximum value, and the smallest is the minimum value. So the important step is this first step. Okay.
Okay.
So this is the method to find the maximum or the minimum value with the constraint c equal to k with the constraint. So this is there is a constraint. The first step is to find x, y, z and lambda. Start that these two conditions satisfied. Then f equal lambda delta c and c equal to k. And then the second step is to get all the values, at all these points we get in the first step, and compare all the values. Okay. If we write the vector equation, this equation in terms of components, then the equation in step 1, in step A becomes this four equation. The first equation fx equal lambda cx, and the second is fy equal lambda cy, and the third one is fz equal lambda cz, and the last is the constraint c equal to k. This is a system for equations in four unknowns. But it's not necessary to find the value of lambda. We just need to find x, y, and z. That's okay. That's what we need. For functions of two variables, the method of Lagrangian is similar. For two, here is for three variables. For two variables is similar to the method with the three variables. Okay. So if you want to find a constraint problem for a maximum or minimum value, we have to use this for function. If it's a three variable case, so please write this one. Write this one in the notebook. Maybe we are using it in the 40. Okay. Yeah, it's okay.
Yes.
Okay, sir.
Okay, thank you. Find the extreme value of f subject to the constraint. We look for values. Here is for three variable case. No, two variable case. So for two variable, there are only three functions. It will be easier than three variables. This is for two variable case. Okay. Here is an example. A rectangular box without a lid is to be made from 12 square meter of cardboard. Find the maximum volume of such box. So first, we can let the XYZ to be the length, width, and height respectively. And then we can get the volume. And get the air. Yes. And the volume will be the volume of the function will be V will equal what? Because XYZ is the length, width, and height, so the volume will equal what? X multiply Y and multiply Z. So it's equal XYZ. And for the air, it will equal, because there is without a lid. So there will have five parts. Yes, have 5 parts. So the air will equal since there are only 5 parts, so we have x multiply y, because there this part don't have. We only have without a lid, so there is x multiply y is only 1, and for the other 2 is 2 parts. And for x multiply z is this part, and this part there are 2. Yes, and yz there are also 2. Yz is here, this one, yz, and there another part, yz. Yes. So this is the air. Understand? This is the volume. This is the air. Okay.
Okay, sir.
Okay, so we have this these two functions. The first one and the second one, and this is the constraint. And we should find the maximum volume, volume with the constraint. This one with this constraint. This constraint. Okay, so we can use our Lagrange multiplier method. Use our Lagrange multipliers method. So we get delta V equal lambda delta C. We get this one. Delta V equal lambda delta C. So this is the Lagrange multiplier method. Okay. Are you okay?
Yes, sir.
Okay. With this one, we have 4 equations. Yes, you have. We have 4 equations. I have let you write in your notebook the 4 equations. And the first equation is Vx equal lambda Cx. Vx equal lambda Cx. Another one is Vy equal lambda Cy. And the third one is Vc equal lambda Gz. And the last one is this one. The last one is the constraint x 2x xz plus 2yz plus xy equal to 12. And we have 4 equations. 4 equations and 4 unknown x, y, z, and lambda. So with this one, we can get the value x, y, and z. So Vx will Vx with we know C V equal this one. So Vx will equal Vx will equal what? V equal this one. So okay, we do it together. Vx it means the partial derivative with respect to x. So here v is here. So the partial derivative will be equal yz, yz. Yes. And then for g, we cannot see g here. We take this one and here. So here Vx will equal yz, and lambda multiply Gx. G is here, and its partial derivative for x will 2z plus y. Yes.
Yes, sir.
Okay, and then the partial derivative for y, this one for y is xz. This derivative for y is xz. And here for the derivative for y is 2z plus x, 2z plus x, and then multiply lambda. And the last one for the derivative for z is xy, and it will equal lambda multiply the derivative for z here. It's 2x and 2y, 2x plus 2y, x multiply. And then this one we don't need to change and the right case here. Then with this 4 equation, we can get the value x, y, and z. So here, there are no general rules for solving the system of equations. Sometimes some ingenuity is required. So here we can find the second multiply x, the third multiply y, and the first multiply z. Then the left side of this equation will be identical. So it will be like this one. So the first multiply x will become this one, and the third multiply y will become this one, and the fourth multiply z will be this one. Yes.
Yes, sir.
So we can find the left side is the same. The left side is the same.
Yes, sir.
Then we can find from the first and the second, we can see 2xz, 2yz, and xy is the same. So we can get x equal to y, x equal to y. Yes?
Yes,
So this is the same. And this is the same. And this is the same. This is the same. So this one will be equal. Yes? So
yes,
x
sir.
from this one we can get x equal to y. And from these two equations we can find no, this one, these two. The left side is equal, and the first one is equal. The first one equal, yes. This one equal this one, yes.
Yes, sir.
And we can we know that this one will equal this one, yes.
Yes,
And then we take y outside, and then we get x equal to 2z.
yes,
Yes.
sir.
So we get
Yes,
the
sir.
result. So AK, we get this one. So here we can get no, not here. Yeah, x equal to y, and y equal to 2z. Yes.
Yes, sir.
Okay, and then we take this in these two results. Take these two results in the equation 5. In the equation 5, we can get this one. 4z squared plus 4z squared plus 4z squared equal to 12. We take the equation 5. Where is equation 5? So this is the equation 5. So here is the equation 5. So we take x equal to y equal to 2z in this equation. You know, x equal to 2z. So this one will become 2z. So it will become 4z squared. Yes.
Yes, sir.
Then this one y also equal to 2z. We take here is also this square. And the last one x multiply y. So it's 2z multiply 2z. So it's also 4z square. And then the right side is 12. 12. So we get z equal to 1. Z equal to 1. Because this is 12 z square equal 12. And then x and y equal to 2. So this is the final result. Okay?
Yes, sir.
Okay. Okay. This is for one constraint, and the following is for two constraints. Two constraints. This will be more difficult. Okay. Can I explain? Suppose now that we want to find the maximum or the minimum value of a function f subject to two constraints. Two constraints. The first one is this one, and the second one is this one. So there are two constraints. Suppose f has such extreme values at the point P. We know from the beginning that this section at f is also gonal to C at P. So C is a plan. Which plan is in the direction of U. Here is not U. Here is plan. Intersection with F. So here C. So here is not easy to understand. But we also know that this one, the delta G is also linear to G, and delta H is also linear to H. Here is easy. Since this one is is orthogonal to this surface. And this one also orthogonal to this surface. So this one and this one are both orthogonal to the to this one, to C. This is not easy to understand, but I haven't find a figure. So we just need to know the following formula. Okay. Okay. Here it's not easy to understand.
Yes, sir.
Okay. We just need this one. We just know this one. Here. For two constraints, we have to use the method of Lagrange multipliers with this formula. The delta F will equal lambda multiply delta G plus mu multiply delta H. So this one is important. So please write this one in your notebook. Here it's not easy to explain. Okay. Are you okay? Can I finish this formula?
Hello.
Yes, sir.
Okay.
Hello.
So from this equation, we will get the following components. Because there is 5 variable for x, y, z, lambda, and mu. So there will be 5 equations. We have to get the partial derivative with respect to these 5 variable. So the first one is fx for x, and the second for y, and the third for z, and the fourth for lambda, and the last for mu. For fx equal lambda gx plus g mu hx. The second for y, fy equal lambda gy plus mu hy. And this is for z, fz equal lambda gz plus mu hz. And this is the first constraint, and this is the second constraint. So here is the formula is easy. But the explanation is hard to get. Okay.
Yes.
Okay, sir.
Okay. So example, find the
Hello,
maximum.
teacher.
Haven't finished?
Hello.
Yeah. Any problem? Yeah.
Hello, teacher.
Yes.
Class is over, teacher.
Oh, okay. Okay, we finish here. Okay.
Yeah.
Okay, we finish here. Okay. Okay. So the following that Harris will give you. Okay. So I
Yeah.
reach 39, page 39. Okay. Okay. Goodbye. We have finished.
Right.
Thank you.
Thank you, sir.
Okay. Okay.
Okay. Bye bye, teacher.
Bye bye.